This video is for physics and AP Physics. This is our quick introduction to Newton's three laws. So the idea here is we're going to briefly go over Newton's three laws. It takes about 20 minutes or so, and then hopefully you'll have an okay understanding to have a chance to be able to do our free body diagrams correctly and solve our problems down the road. And this will give us some examples to reference back to when you guys get confused on some stuff. Okay, so the first thing that we're going to address is Mario Ball is sitting here on this desk. Okay, when Mario Ball's sitting there on that desk, there are definitely forces acting on him, right? Okay, there's gravity pulling down, and there's the table pushing up. But the result of all that is that it just adds up to zero. The stuff balances out. He's in equilibrium. All right. Another example that we're going to reference here is Mario Ball in space. So this just helps with the visual. I could do this thought experiment anywhere, but to help with it, we're going to be out in space far away from the Earth. And what I'm going to do is I'm going to throw Mario Ball, and then the moment that I let go of Mario Ball, I disappear, and so does everything else in the universe. Okay, it was like a super amped up Thanos snap. Everything in the universe is gone except for Mario Ball. Yes, I know we still need to have a reference point. So we have some massless reference point, okay, to make his motion make sense, okay? But everything in the universe disappears. So I throw Mario Ball, after letting him go, poof, everything disappears. In that case, there are no forces at all acting on Mario because we've gotten rid of the universe. So the question is, what will Mario Ball do? Well, if you answered that he's going to keep going at the same speed and in the same direction forever, you're right. Okay? He's going to keep doing the same thing. Okay? He's going to have a constant velocity, same speed, same direction forever. That is also what happens here even when we have forces, but they add up to zero. Or if the object, let's forget the space example. Let's have Mario, hockey puck Mario now, and now I'm a hockey puck, or sorry, I'm not a hockey puck. I'm a hockey player, and we're going to go ahead and hit this, okay? And imagine when we hit hockey puck Mario that there's an infinite plane, and somehow there's still gravity pulling down and the ground or the ice pushing up, but there's no friction. So we have an infinite plane of frictionless ice. I could call it frictionless sandpaper, but that visual won't work as well. So frictionless ice in all directions, infinite plane. So if we hit hockey puck Mario, what would he do? Keep going. Same speed, same direction forever. Assume there's no walls or anything. Again, an infinite plane of frictionless ice. He would keep going, okay? You've probably heard this. This is Newton's first law with examples. You've probably heard this expressed as an object at rest stays at rest. That was Mario Ball sitting on the desk unless acted upon by a net outside force. Or object in motion stays in motion unless there's a net external force. Something along those lines. You do not need to memorize that or spit that back at me. All you need to know is the idea of Mario Ball sitting on the table. Okay, if the force is up to zero and he's not moving, he's going to keep not moving. Okay, or hockey puck Mario / Mario Ball in space. Okay, if the force is up to zero or there aren't any, okay, acting on the object, it's going to keep doing what it's doing. Same speed, same direction forever. Or it'll just sit there. So that's the first law. Now, the second law covers the first law. So eventually, once you're comfortable with using the second law, it does a lot more, but it also does include the examples that we just talked about. So it covers the first law. And the second law is an equation that you may have seen before. And that is if you sum up or add up all the forces acting on an object, and these are external forces or outside forces. I won't always write this, but if you sum up all the external or outside forces acting on the object, it'll be equal to the object's mass times its overall or net acceleration. And we can also look at this broken down to various directions as well. Okay? I'm going to draw that a little bit better. That is a capital sigma. And it looks like that. That's my somewhat neat version of it. Eventually, it's going to turn into that. So all of these mean the same thing. They mean add up, okay? Add up something. And at some point, you'll get those in a math class if you haven't had them yet. Okay. And let's go ahead and apply this second law here, this F equals ma, the adding up of the forces equals the mass times the object's overall acceleration. That's what I mean by net, total or overall, not fishing nets, okay? And external meaning outside, not inside the object. There's lots of intermolecular forces. We'll learn more about why we don't worry about those after we have the third law, okay? Somewhere down the line, though. We're going to learn the third law today. All right, so let's go and apply this to our Mario Ball sitting on the table. If I add up the forces acting on him, and forces are a vector, they have units of newtons, okay, but the direction does matter. So there's gravity pulling him down, Mario Ball down, and there's the force of the table pushing on him, or the desk pushing on him up. And that up arrow and that down arrow, they're the same size, okay, and they're going to add up to 0. Because if we put a sign on it, we'd have like 5 newtons going up, maybe 5 newtons going down, completely made up that number. That 5 minus 5 will add up to 0. And if the left side of this equation is 0, yes, Mario Ball has a mass, but to have this equal 0, the acceleration would have to equal 0, which means he stays put. Okay, that covers that. Now, what about the hockey puck Mario or the Mario Ball in space? Well, in both those cases, same idea. The forces add up to 0, therefore the acceleration, the overall acceleration has to be 0, which means he's going to have a constant velocity. So if he's already moving, he keeps moving, same speed and same direction. But we don't always have accelerations of 0, right? So this covers other cases as well. If we have a net force in a direction, for example, let me get a book out here. A lot of times I'll have an opener where you shove a book. You may or may not have had that, okay? But I'll say, make that book on your desk move, okay? So what do? You come over and you do that kind of thing, all right? And let's neglect friction for a minute. How did I get that book to accelerate? It's initially at rest, and then I'm going to get it to move. What did I do? I pushed on it, right? Okay. And a force, you can think of a force as a push or a pull. That's okay. It's not going to mess you up anytime soon, okay? So we pushed on it or we pulled on the object, and as a result of that, if we had no friction, let's make it as simple as possible, if we had no friction, all of a sudden there's a force going, in this case, towards the camera that wasn't there before, okay? Right now it's at rest. The forces add up to 0, acceleration 0. Now all of a sudden I put a force going that way. Well, if there's no friction, it's definitely going to start to accelerate that way, which means if it's at rest, it's going to start to move faster and faster towards the camera. All right, so that's the idea here, is that if we look at the adding up of the forces and we get something other than 0, that will tell us our direction of our acceleration. But more than that, we'll be able to actually solve if there's numbers involved in this. So this does cover big ideas, and you can use it conceptually, but we're also going to put it to use with numbers. So that's Newton's second law, okay? And again, once you get comfortable with this one, it covers the first law. Now let's go ahead to the tricky one, Newton's third law. All right. So you're going to have to use your imagination here a little bit, okay? Most years I skate around the building. You may have seen me, and on this day I wear skates, but I don't have my skates in the room right now. So I'm sitting on a wheelie chair, okay? Imagine I'm standing on skates. I don't like the way I'm sitting on the wheelie chair. Oh, that's much more comfortable. All right, so I'm sitting here on a wheelie chair. I can move around here. I can roll, okay? And what I'm going to do is I'm going to push on this wall. When I push on this wall, which way am I going to accelerate? Am I going to have an acceleration of 0? Am I going to accelerate toward you guys, the camera, or am I going to accelerate away? So I'm going to push in this direction, I promise. I'm pushing that way towards the wall. Which way am I going to accelerate? Go ahead and give me your answer. All right, so let's go ahead and do it. So right now I'm at rest, and we're going to neglect friction. That's why I'm on the wheel. So pretend there's no friction for simplicity. We'll get to friction eventually. All right, so I'm going to go ahead and do this. Forget that collision at the end, okay? So when I first pushed on the wall, while I'm pushing on the wall, I accelerated this way. So I'm not worried about the end of that trip. Just while I'm in contact with the wall, I'm going faster and faster that direction. So that's the direction of my acceleration. So it looks like now that we have some sort of contradiction, because I pushed that way. I pushed towards the wall, yet I accelerated the other direction. Take a guess as to what's going on here. Take a guess as to what's going on here. Why was I able to push that way, yet I accelerated the other way? All right, now the surprising thing for many people, when you push on the wall pushes back on you. So if I push that direction on the wall pushes on me the opposite direction with the same magnitude. So if I push with 3 newtons away from the camera, the wall's pushing me towards you guys with 3 newtons, at least while I'm in contact with the wall. And that's the force that allows me to accelerate towards the camera. All right? Now, sometimes people get confused right from the get-go here. That force of the wall pushing on me was what I would add up here. And that would be it if there's no friction going towards you guys. That force of me on the wall the other way would not be added up, because otherwise we'd get 0. right? And then we'd have a problem again. So that force of me on the wall is going the other direction, and it's acting on the wall. So that would be if we were summing the forces for the wall. So now the question is, I'm pushing on the wall that way, different object, right? It's adding up the forces. Why is the wall not accelerating away from the camera? What do you think? Why is the wall not accelerating away from the camera? All right, well, there's a lot of other forces acting on the wall to keep it where it's at, okay? It's connected to the floor. It's connected to the ceiling, right? We've got friction with the ground. If you said friction, that's great, or that it's connected. You may have also addressed that it has a much, much bigger mass. Therefore, it would have a much, much smaller acceleration. That's good thinking as well. But it is anchored in, right? There's lots of other forces acting on the wall that would not show up when we're summing up the forces acting on me. Again, with no friction, the only thing acting, without friction, the only thing acting on me in this direction towards or away from the camera is the wall pushing on me. Right? That's it, okay? Not me pushing on the wall. That would go on a separate problem for the wall. And eventually when we do free body diagrams, those forces that we just discussed would go on separate free body diagrams. That'll be coming up very soon in our courses. Okay. I think that's about it. I'm going to provide another example here. Let's say you're standing in an elevator and you're standing on a scale. The force of you on the scale is the same thing in terms of size as the scale on you. That will be true no matter what happens in that elevator, okay? Or me pushing on the wall will have the same size as the wall pushing on me. And if I'm doing that in an elevator or standing on a scale in an elevator, even if the elevator is accelerating and a black hole pops up in the corner of the elevator and, I don't know, I'm on fire, okay? None of that matters. The force of me on the wall has to be the same magnitude as the force of the wall on me, regardless of what else is happening in the problem. Okay? It will always hold for everything in the universe. This also means that the force of gravity or force of the earth on you is the same thing as you on the earth. We'll talk about why you don't notice the earth accelerating up towards the pen when I drop it eventually. This also means that the force of the sun on the earth, okay, the gravitational pull of the sun on the earth is the same thing as the earth on the sun. And every other object in the universe. We'll deal more with gravity eventually. For AP, very, very, very soon. For physics, it'll be a little bit down the line. But we will deal with those ideas again. If that's a little confusing to you, we'll absolutely discuss those again. All right. That was your introduction in about 20 minutes, I think. I can't see the timer from here, but I think that was about 20 minutes on Newton's 3 laws. So we will be referencing Mario Ball in space occasionally, the Mario Ball sitting on the desk. Definitely these ideas of summing up forces, like getting a book to move, looking at a direction where there is some external force that is not balanced out by something else. And then Newton's third law, the idea that if you push on the wall pushes back on you. Oh, another example of that is if you get punched in the face. The force of your fist on the face is the same as the face back on the fist. Okay? Doesn't mean the results will be the same for the two objects, but the magnitude of the forces are the same. The directions are opposite. Okay, that was it.